All right. So, today I'm going to talk about a very strange topic. Because everything else so far, as you know, has been exceedingly mundane and predictable. This will be our final topic in analysis variance. We're going to move on to regression and correlation, which has its own charms. We're going to talk about unequal cell sizes. Wait, I was in the wrong place, so it's not advancing. Okay. I have never ever mentioned how having unequal number of subjects per group. I've just said n equals, we just had in the quiz example, n equals 3. So the designs that I'm doing here assume equal n's. Except for the most basic one, which is one-way analysis of variance, it doesn't assume unequal n's. Or equal n's, it can deal with unequal n's. So what if you do have unequal n's? That's, in fact, a very common problem. It's a common occurrence when you go to the thesis conference next Friday, which you should all go to. Starts at 1 o'clock. 8 psychology, 5 biology, no waiting. It's going to be great. It's going to be science, like crazy sciencey stuff. It's going to be fun. And you will see unequal ends in all kinds of people's experiments. In fact, I bet every experiment, I'm trying to think, I saw the biology book. The ones that use ANOVA. Yeah, I think they're all, anybody uses ANOVA has unequal ends. And I'm telling you that you need equal ends. And this is not a case of people going, yeah, it's fine. There actually is a way that this is dealt with. And it's transparent to most people, so that's why people don't think about it. Well, one thing one could do, if you really cared about having equal ends, is maybe you can estimate missing values. This is sort of part of a larger discussion. If you have values that are missing, perhaps you can estimate them. And at first that sounds reasonable. When I say something like that, it's pretty clear that it's not reasonable, right? But there are options in any statistics package to estimate missing values using the mean or the median, usually of the cell. So let's say you're missing some values in A2, B2. It just takes the mean or the median of A2, B2 and throws that value in there to make them all even. So you got like 9, 9, 9, and 10. In that case, I would randomly select one out of the ones with 10, and I would just remove it. I'm not going to add 3, I'm going to remove 1, make them all none. Or, let's say it's 10, 10, 10, 10, 11, 11, 11. Well, I want to get 11 in that one cell. I can just take the mean or the median and then do the calculations. Now, here's a question. When you're doing that, though, are you going to look at the cell mean, as I just said, which is then taking the interaction into account? Or am I just going to look at the main effects? There's an effect A or an effect B. Because all these things are going to be affected by the number, all these calculations are affected by the number of observations you have in each cell. So it actually becomes a much more complicated question than you think. It's an odd thing to think about, and typically we don't. But from a theoretical standpoint, it's actually kind of a cool thing to think about. No matter what, you don't, I guess you've lost degrees of freedom or you didn't gain them. So if I estimate a value, it doesn't mean I've now added that I get an extra degree of freedom. That wasn't free, that choice. I put it there. The number was not free to vary. I did it. A friend of mine told me once about getting an article from a journal or sort of getting a review. It's like doing a review, sort of, for a journal. He's a social psychologist, and he got this thing, and people ran it's a questionnaire kind of study. Okay, so they give him a questionnaire. I don't know what the study is, but they have 40 cases, and they did a correlation. Was it significant? So the suggestion from the reviewers was to just collect more data. It's going in the right direction. Go back, collect more data, and see if you actually get a significant effect. If you do that, that's great. If you don't, well, then you found nothing, but it looks like it's going in the right direction, so go see if you can find something. One could argue there that's p-hacking. But anyway, the revision comes back really quickly, like within a day kind of thing, which shouldn't happen, because how do you go collect 40 more data points in a day when you're handing out surveys to people? Like, that takes longer. And it came back, and they just doubled the size of the data set. They just take the numbers and copy and paste them and make it do it again.
Well, would they still be equal then?
No, this is just like 40, this is a different kind of thing, correlation. But what they did is, instead of collecting data, they just estimated 40 more data points. Yes. Now, they weren't doing this in any sort of nefarious way. They just didn't know what the hell they were doing. And two things. First of all, you can't do that. And secondly, then they did this with, they said, instead of having 39 degrees of freedom, now we have 79 degrees of freedom. Oh yeah, that's significant. Yeah, no, you can't do that. And again, my friend was convinced that these people were not doing this out of any sort of, they weren't trying, because they simply did it. Like, it wasn't like they said, so we are just double the data set size, and no, it works. It's like they clearly said it in the paper, so obviously they didn't know what they were doing. There wasn't some, it's like today when I said to my son, did you take all that money that was on my dresser? He said, yeah, honestly, it was me. And I said, that's called stealing. He said, am I a thief? I said, you are a thief. You are actually a thief. I was going to give you money anyway. You don't take money. Right? It's the same sort of thing. Like, these guys are like, yeah, so we just made up some more numbers and threw them in there and it worked. You can't do that. That's not how it works. So that's what these people actually did. But they even had the gall, or the lack of understanding, to say, oh yeah, degrees of freedom went up too. No, they did not. At least if you do that, say, well, we made those other ones up, so we're going to keep the same degrees of freedom. At least then you go, okay, you're statistically sophisticated, you're just scientifically stupid. Right? But at least that would be. So you don't get degrees of freedom when you make up numbers. The numbers aren't free to vary. So in fact, most of the time we don't estimate missing values. We usually just ignore them. Okay? There's going to be rare occasions where you might, but it's going to be vanishingly small.
What do you mean you ignore them?
You pretend they aren't there and do a different kind of analysis, which I'm going to talk about in a second. So, there's other ways to do it that are actually a little better. In fact, the way you should do it, really. And when I've been talking about sums of squares, I've been talking about something called type 1 sums of squares. Okay? We do it because it's the easiest way to teach it. And conceptually, they're all the same thing. But at the basis of sums of squares, it's actually, well, they're called sums of squares, and they're square deviations from means. They're not really defined that way. They're actually defined through matrix algebra. And I'm not going to put you through that. Because it almost made me quit graduate school. So, okay. I was just putting big matrix things, just writing numbers. I had no idea. I don't know, 1, 2, 1, 1, 0, 0, 1. I had nothing. Matrix algebra was the death. That was the math when I went, okay, that's enough math now. That's enough. I can do all kinds of things, all kinds of really cool calculus and stuff, but that, no, can't do that. And I'm in PhD 1, and my prof is like, you've all done matrix algebra like in high school, right? I'm like, I took 3 math courses in grade 13. What did matrix algebra? And we're all sitting there like, oh. So like, oh, here's a book. A photocopy of the book for you. You just read it. But eventually you understand matrix algebra. Your PhD students. Shit. smart enough to be here. The nice thing was we all felt that way, so it was good. And we had there was a math major woman with a math undergrad degree in our lab. Strange story, she's a math undergrad degree and she was this PG in psychology. Long story. But the next day, everyone's like at her office, going, Chris, can you help us? And she was speaking such a different language of math, it really was no help, even though she tried. So really, it's defined through matrix algebra. The notion's the same, the deviation of squared deviations from means, but that's actually not how computers calculate them. They're doing matrix algebra. And they actually work really well if the ends are equal, type 1 sums of squares, and they mostly work for one-way analysis of variance only. And in fact, type 1 sums of squares don't work well at all in the presence of an interaction. Wait, what? Yeah, I'll show you in a second a comparison of different types of sums of squares and the fact that they come out with different numbers. And the weird thing about type 1 sums of squares, let's say you're doing it for A and B and A by D. First of all, the interaction f's up everything. And secondly, if you calculate the type 1 sum of squares for A first, it's different than if you calculate type 1 sum of squares for B first. The order matters. It's just believe me. Just believe me. Pretend you're Catholic and I'm Pope Dave. Okay? It's the case that if you calculate one first, because what it does is it calculates. Okay, I'm going to see if I can explain this. Let's say there's variance that's shared between A and B, an interaction. That's what interaction is, right? So if I do A first, it calculates A. It calculates add mean square due to A, but it's also got A and B in it. Then I do B, and it gives me a value. But if I do B first, it's going to give me B and B and A. Then if I do A first, so that's why the order you do the calculations in will matter. So that's not good. So they're also, and when we have unequal cells, they don't work at all. Well, there's got to be another type. There's a type 2. Type 2s are good when they can deal with missing values. They're fine with unequal cell sizes. And what they do, in fact, is they do unique incremental amounts of variance, which is great. So they, A on its own, B on its own. Not A and also A and B if I feel like it. Type 1 sums of squares are quite capricious that way. Whereas type 2s, not so bad. But if there is an interaction, again, they have some trouble if there's an interaction and there are different cell sizes, different unequal ends. Oh, well, that's not good either. Because they'll do A on its own, B on its own, but then when they do A and B, they also include, you calculate A, that's right, they calculate B, fine. They also calculate A and B, which includes A and B. Oh, shit. Yeah. They have their uses, in fact, in regression. We use them all the time. And there's a reason we use them in regression, which we'll talk about. So type 2s are kind of a bust for ANOVA. Type 3s, if you've noticed when you've done your calculations on SPSS or PSPP, or if you've used JASP, which I've just become enamored with, when it does the ANOVA, it says type 3 sums of squares. Type 3 sums of squares work the way sums of squares you think should. You probably don't know if there's an interaction or not, because that's, if you knew, you wouldn't have to do the experiment. Type 3 sums of squares, you're fine. They do A on its own, assuming there's A. They put it this way. What they do is they calculate A given B and A and B. B given A and A and B, and then A and B given A and B. So unique variance. So in my presenter notes, the word just says yay. It works. And they can deal with unequal cell sizes. I've told you about type 1s mathematically, but what your computer's doing is type 3s. Now the nice thing is if the cell sizes are equal, type 1 equals type 2 equals type 3. But your cell sizes in the real world usually aren't equal. So if the m's are equal, type 1 equals type 2 equals type 2. I'm just going to show you, I just downloaded this, or took a screenshot. Hopefully this is viewable. Okay. So this is all the analysis did the same way, and this is, we've got an A and a B and A by B, so we've got a 2 by 4. Okay? And this is with unequal cells, unequal cell sizes. And so the type 1 sum of squares, look at the differences. Look at the B sum of squares. And look at the A by B's. They're all the same. The interactions are all the same. That's great. But look at the main effect. And it's telling you it's doing A, then B, given A is already in the model. A by B, given A and B. Like I was saying, the order matters. Here it's okay. It just doesn't include the interaction. This is what we like. This on A on its own, B on its own, A and B on its own. So it shows you that the reason I can tell you about type 1s because they're easy to understand, but type 3s are what's going on behind the scenes.
So this is going to be the model we're going to use basically.
You always use type 3s.
Okay.
You have to. And frankly, you don't really calculating type 3s involves doing matrix algebra. We get such a very good approximation doing the stuff I've taught you with the little summation signs and that we're okay. The thing is, we're not actually, so conceptually, that's good. But the important point here is that really what's happening behind the scenes is type 3s of a computer program. What do I, oh, there's courses of type 4. No, there is no type 5. But there's a fourth type of sum of squares. What if we have an empty cell? So we got an A by B, A1, so yeah, like something, well, I think I have an example. So the problem with empty cells is there's no unique solution. Because you don't know what belongs there because there's literally no data there. Like, okay, here you go. There's an empty cell. What goes in the bottom right there? That's a mean. That's made up of a whole bunch of observations. So 10 observations, let's say here, so we get 10 observations in A1, B1, 10 observations in A2, B1, 10 observations in A1, B2, and oh, we didn't collect any data here. Well, we want to see if there's an interaction between A and B, and an A effect of B. What goes there? How? It's intriguing. Explain your ideas.
Well, if we have this structure on the model,
Yeah, sure. So what's the model here?
so alpha plus beta plus
Yeah.
alpha beta plus epsilon.
Yeah. So we'll not even worry about
Yeah.
this because that's individual differences.
Okay, so then
Okay. So what'd you do next?
isolate. I don't know. Is this completely?
What you're coming up with is a solution. And you're trying to work out a logical, reasonable solution. And there's nothing wrong with that.
So then if the alpha beta effect is together, then we just isolate that one,
Yeah.
and then
So let's assume there's an A effect.
yeah.
Because look, 4 and 2, 2 and, well, there's nothing there. I guess we have to guess and put a number there. Oh, or is there a B effect? 4 and 2, 2 and 2 and 2? Oh, 2 and 4? What was 0? What's wrong with a million? What about 3? minus pi.
Happy Friday.
Yes, it is. That's right. I'm waiting for the 71st of February for E-Day. Yes. Anybody got that? It'd be pleased. So, I know, Dana, you're trying to be reasonable about this. There's no reasonable answer to this.
There is no way to isolate the AV effect.
Because
and
I
find
don't,
it with
how? You can't. There's no unique solution. There's an infinite number of possible solutions.
Something you can put in would be like a letter to hold in place, and then you're just finding equations where you can substitute any.
Exactly, but there's an infinite number of possible
Yeah.
solutions. Type 4 sum of squares actually come up with solutions. In this case, it would probably get confused.
Yeah.
If you had like a 5 by 5 and there was one missing cell, type 2/4 sum of squares kind of do what you're talking about. Kind of do what you're talking about, which is like say, okay, we found all these other effects. Let's assume everything works that way and combines the way we guess, and then we can get A3, B4 where we have nothing. We can put something in there. Right? So what type 4s do actually is what you're trying to do.
So if you have like multiple cells and you have the one cell,
Yeah.
is it kind of like they're putting like that cell is X, and you know that
Yes.
all these add up to this, so X plus this plus this.
In
equals
essence,
X.
that's what happens. Yes.
Okay.
Yeah. Except it uses many matrix algebra that I barely understand.
So how do we do it?
You don't.
Wait, what?
You don't.
Well, then what are all those, the thesis students gonna do?
No, they don't have empty cells. They have unbalanced designs and use type 2 sum of squares. Nobody has this. Somebody has this, we would give it. Exactly. Also, their supervisors wouldn't allow this to happen. How would you analyze this actually? Like if you were approaching this, you're taking a look at this and going, okay, what am I going to do? Because there is a way to tackle this problem of looking at this that is practical. And type 4 sum of squares isn't an answer to this. It would come up with a different answer every time you ran it. What? Yeah, it would. So, well, it would probably come up with three different answers. And none of which you could argue that is wrong or right. Because you have one missing cell. What would you do to analyze this data? Because there's actually, yeah, Sean, there's a very simple answer.
Would you just run it all 3 times and assume that all 3 could possibly be
And one will assume an A effect, one will assume the effect, and one will assume an interaction. So that's not good. Nice, I guess. What else? Other possibilities.
Go back and get the information.
Well, that's one way to do it. Let's say you can't. Let's say it's March 21st and the thesis conference is March 22nd. You haven't talked to your advisor yet because you're a lazy
Can I
bastard.
have an example?
Yeah, you don't get extensions on your thesis. That's not
Don't
great.
get a fee if you drop.
Yeah, you get a withdrawal with it, and we keep your money. You get a 0. So something practical, not that solution or that one. Something that actually would work. Because there's a very simple answer here, and it would be okay. Oh yes.
Would you just put a 0 in there, or
Yeah, but why 0? Why not a 43?
because you don't have a value?
Yeah, but 0 is a number. It's different than nothing, right? No, that's a nice try. It's wrong, but it's a nice try. Other thoughts? Sean?
Could you just do like separating into 2 different things where you have like A with B1, B2, and then B1 with A and A2, and separate into that?
You're getting
2
close.
different tests.
Well, why not just do one? There's a way to do this with one test.
Okay, and?
Just do a one-way ANOVA with 3 groups.
Oh.
I can't tell you if there's an A effect or a B effect anymore or an interaction, but I can at least tell you the 3 groups are different or not. I can at least do that.
So just ignore the whole.
And yeah, just say, I didn't do that.
Just ignore the whole interaction.
Yeah, or A effect or B effect. What you're doing is now comparing 3 groups. But at least you would have something. Right? At least you would have something. And that's what you do in this situation. Right? So if we have, and there have been situations when people didn't have all the data collected before the thesis conference, because they didn't, I'll just say that. So he's like, okay, here's a preliminary thing you can do. Just do this. Now you can't talk about interactions or main effects in your talk, because and make sure you get this all done before you wake this up. Person whose name I'm thinking right now. Guy met with me once in October. That's it. That's it. And then like a week before, he's like, so should I start collecting data? It's like, yes! Yes! See, people wonder why we changed that requirement to make it higher up to get into that's one of them. Because those people that did things like that were always people that got like, they just got a 60 in the third year stats and methods. It's like, yeah, I don't think that's good. So, anyway, just saying. The shark. I did have an honor student one year who analyzed all his data the night before. And it was gorgeous. It was one of the neatest experiments ever. And only one person could do this, and it's that guy. He's one of those guys you see about it every so often. He just doesn't take notes. He just sits there in class, and he used to roll cigarettes. That's what he'd do. He just roll cigarettes. And he talked and looked a lot like each time anybody, but he wasn't. But he was there with money, Shosholo. He rolled in. He sold me a computer once. He said, do not call for customer support. So, I'm entirely sure where the computer came from. Do not call for customer support. Okay. So, that's what I do here, is I just do that. I was telling you the other day about consulting for people in grad school, and this is what happened. They had a whole bunch of empty cells. If you have one empty cell, and it's like a 5x4, and you can't collect any more data, it's not great, but I would go say, yeah, we could probably do something here. But these guys had like a 4x4, and they had like 5 empty cells. It's like, guys, you're missing all your data. You can't even do this. We could do, and I suggested, we could just compare all groups. But we think these two things go together. Well, then you should have collected more data. Yeah, Dan.
Okay, so when there are just simple values missing, the type 3 ANOVA.
Take the type 3 sum of source is
it's
fine.
fine.
Yeah.
We don't need to do it.
Yeah.
But when there is an interaction missing, then use.
Well, when's an empty cell?
Right.
That's what this is. This is an empty cell.
Okay.
You don't want that.
Which is a lack of data about a certain interaction combination.
Yeah, exactly.
Then we just
Then we
discount it.
then just turn this into a one-way ANOVA. That's what I did. Or in fact, a better solution is go back and collect more data.
Yeah.
Yeah. Because I like when you said interaction there, because that's what this is. It's an interaction of A and B, but we don't actually know if there's statistically, an interaction. But that's what I do here, is I say, please go get some more data. And if you can't do that, just compare these 3 groups. But now you can't talk about A and B. You can talk about them as being 3 different groups. That's all you can do. Right? And then you get asked the question, why didn't you do?
So does this basically point to like a poor design in the beginning?
Yeah,
Like when
it's
something's
poor design
started?
or poor sort of protocol. When you run an experiment, before you start any experiment, no matter what science you're doing, you write down a protocol. This is what I will do every time I run my collect data. And you write it step by step. I do this, I do this, I do this, I do this. And whenever anybody says to me, should I run this condition on this day? It's no. What if by some strange happenstance, one day is way different than another day? I don't know how. What if it's way different? Let's have some of this group here on this day, some of another group here, some of another group, and we'll do it random. So it's usually poor implementation of the design. It could be poor design, it could just be they didn't even think about this.
Like you would think you drew your design on the first day and you were like, oh, look, I have to do B2, A2.
Yeah. That would be, that's just, that would be poor design. Usually, like I said, that's quick protocol implementation.
Okay.
Like you have a protocol and you say, this is what I will do each day. When I run my study, this is what I do. And the other advantage to doing that is that becomes your procedure section of your paper. You write down literally everything you do in exact order. And then on the first day, you find out, oh shit, I have to do that too, so you write that in. And that happens to everybody. It's not like it doesn't matter if you're measuring something to do with plants and their growth, or you're watching birds in an aviary, or you're giving questionnaires to people on assigning guinea birds. You write down everything you do every day before you start. And at first it seems silly. Like I always get my students to do that. They think I'm crazy. No, write down what you're going to say to people. What? Write down what you're going to say to people. Because just do it the same way all the time. Because if you don't do that, you're going to forget one day to say X, Y, or Z. Questions about this? It's crazy. It's a weird topic, but it's kind of, it makes you feel better about yourself because you know I never do that. You're thinking to yourself. Just good. So it can make us all feel superior to that one guy who didn't finish his thesis. Well, he did finish it. He just finished it late.